My name is James Weaver, and I work for Pivotal. I'm a developer advocate for Pivotal. Julie, could you give me some water here? And there are my coordinates. I tweet at JavaFX Expert. So if you want these slides, which are web-based slides that have a lot of, it's got a lot of good resources and things in there that I'm not able to cover in 20 or so minutes. So I would recommend actually getting the web-based slides and then after the talk sometime just kind of exploring some of the resources. So JavaFX Expert, written several books mostly on Java and IoT kinds of things. I work for Pivotal. Pivotal's mission is to transform how the world builds software. We curate Spring. We're the stewards of Spring, which is a framework that makes it really easy to create applications, particularly ones that are going to run in the cloud natively. We also have a cloud platform called Pivotal Cloud Foundry. It's based upon open source, and it runs on all the major cloud providers, giving developers a consistent cloud experience. We also have Pivotal Labs all over the world, one which is a couple blocks away here in San Francisco, and where we bring customers in, pair program with them, teach them agile processes. And then we also, the new kid on the block is Pivotal Container Service, which is production grade Kubernetes, if you're familiar with the Kubernetes containers. But my favorite thing about working for Pivotal is our principles and practices. We have 5 of them, 3 of them are here, and the third one is my favorite, be kind. And I feel like I'm a pretty kind person. I don't really require a company to tell me to be kind, but it is really cool to work for a company whose one of their prime directives is to be kind. And in this day and age, for God's sakes, let's be kind to each other and treat each other like we want to be treated. And so, and also I'd like to invite you to a spring party. It'll be Spring One platform at Moscone West, just a couple blocks from here. So colleagues have talked about why use a quantum computer, because there's stuff that's really, really, really hard. So we want to be able to do it exponentially faster. So a guy by the name of David Deutsch in '85 kind of proposed an algorithm, had a problem and proposed an algorithm called, oddly enough, Deutsch's algorithm. And it's literally the hello world of quantum algorithms. Here's the circuit. You've got a couple of qubits coming in. Colleagues have talked about Hadamard gates. That middle thing is an oracle. It's a black box. And then we have another Hadamard coming out. We're measuring it, and we're throwing the one down in the trash. And so we're going to talk about that. But let's talk about the problem, first of all. The problem, Deutsch's problem, is that you have this function, and you want to be able to pass either a 0 or 1 into the function, and then you want to be able to tell whether it's a constant function or a balanced function. So constant would mean no matter what I passed in, it's going to bring me the same thing out, 0 or 1 every time. If it's balanced, if I pass in a 0, it's going to bring out a 0. And pass in a 1, it's going to bring out a 1, or the reverse. So we've got 4 different functions there. And so the task is then, tell me, Oracle, tell me, is this a balanced function or a constant function? So there's the Oracle there, the part of it where we have 2 qubits coming in, and so the top wire here of the Oracle contains what's being passed into that function, and then the bottom wire, after the function is applied, then gets XOR'd, exclusive OR'd, with what comes into the bottom wire, and that's how the Oracle calculates the function. Now, this is with all gates and all oracles and everything within quantum computing, they need to be what's called unitary. They preserve the unit norm. They're also reversible. And so you need to have the same number of wires coming in as coming out so that you could then reverse it. And so that's why we see this. There's an excellent lecture by by John Watrous of University of Calgary that really covers some of this stuff well, and I would recommend taking a look at that. So DeutschJozsa Algorithm, how many queries of the oracle do we need to solve? Well, classically, you need 2 to really be able to solve that. Quantumly, we need 1. So why do we need 1? We're going to get into that in a second, but let's talk about how we would query this oracle classically. So we have the oracle here, and the oracle is represented by a permutation matrix. And all gates, whether it's single gates or multiple qubit gates or whatever, can be represented with a matrix. Sometimes not as clean as a permutation matrix, but with a matrix. And then we represent the input, like the 0, 1, and by the way, the least significant bit I'm putting as the top wire here. 0, 1, which is Dirac notation here for a 0 tensored up with a 1, during a Kronecker product with a 0 with a 1. And so this is the vector representation of 0, 1. So we multiply this matrix by this vector, and we come out with 1, 1. And so that's how you would do it classically. And you'd have to do that twice then to figure out which one of those it is. So now how about quantumly? So we use quantum parallelism. And so that's one of the most overhyped kind of things in pop culture, quantum culture. What is quantum parallelism? Well, what it is not trying all the answers in parallel. But what it is, it's more like the classic double slit experiment, where you've got photons coming into maybe a couple of slits, maybe more slits, and then you have these waves then set up interference patterns, constructively and deconstructively interfering to then at the back wall then on the screen you have some pattern, and so the challenge then is to choreograph your pattern, or actually choreograph your slits to where the right answer comes about by constructive interference, and the wrong answers are weeded out by destructive interference. So here's a really cool cartoon by Scott Aronson, and it's all in the guise of the talk, the talk of, the birds and the bees talk, but it's the quantum talk. And so I would recommend going to that. So this is how you would query the oracle quantumly. And so again, it's just going to be once. Not trying all the combinations, it's just once. And so going through this, it's a busy slide, I know, but colleagues have talked about Hadamard gate. Well, this is the matrix for a Hadamard gate, for the transformation matrix for a Hadamard gate. Well, if you tensor that up with itself, take the tensor product of 2 Hadamard gates, then what you get is this. And so that is the matrix representation of 2 Hadamards. So we take the 1, 0 coming in, which is this vector, multiply it by the tensored up Hadamards, and we get this. So that's a superposition consisting of, it's 2 qubits. You just take the square, right? 2 qubits, there's 4, there's 4 in the composite state, right? 3 qubits, there'd be 8 values, amplitudes in the composite state. So anyway, this is a composite state that's a superposition that is at this level of the circuit. So then that's the input into the oracle, this black box that we've kind of walked through. Well, remember this is the permutation matrix for the oracle. So then we're going to multiply that superposition, this superposition, I'm just repeating it here, by the oracle once, not twice, not for every potential answer or whatever, just once. And then we get this superposition on the other side of the oracle. Now you can think of that superposition as a four slits in the double slit experiment, in the, like four slit experiment, spaced out to where they are strategically going to then constructively and destructively interfere until we get, and then here we're multiplying it by the Hadamard's, right? Until we get the light focused, the photons focused on a particular part of the screen, or in this case, to a particular state here, which is 1, 1. And so when we do the measurement, as colleagues have talked about, it collapses, and so there would be 100% probability that that state is going to be 1, 1. Okay, so that's kind of everything that's going on, in the background as far as modeling it with linear algebra. And so there is a really nice quantum simulator. It's a browser-based quantum simulator by Craig Gidney called Quark. And so I've just taken a screenshot of the circuit portion of the 4 different functions possibilities, right? We've got where the input is 0 and 1, and we've got the constant, always 0, always 1, and then here's the balanced, 0 and 1, 1 and 0. And so then these are the circuits in this Quark quantum simulator that represent all of those. So I'm representing maybe from, like here, for example, I'm representing the balanced one with a C0 gate, as colleagues have talked about. And so we'll go ahead and drill into this one. We can click that and open it up into this quantum simulator. And we can see that, that this is the same as the matrix and vector multiplications that we've been doing. So here's the 1, remember we had a 1 qubit coming in? Well, to get the 1 qubit, we do a bit flip, which is this X gate on a 0 qubit. And so now we have that input to the Hadamard's. This is the first superposition going into the oracle. We're modeling the oracle with a C0 gate for the balanced. And then this is the second superposition. And we take the Hadamard's, measure them, and we get 100% probability that that it will be 1, 1. So the question then that this running all 4 of those simulations answers is, why did it just take 1 classically or 1 quantumly instead of 2? Well, the reason is that if you look over here on the right, with when measured what the state was that was measured, here for both of the constants, we see that the state was 1, 0 with 100% probability. The only thing that was different was the phase. So the phase doesn't matter when you're taking a measurement, because when you take a measurement, you take the square of the amplitude. And so in each case, even though the phase is reversed, you take the square of the amplitude, it's going to be 100% probability that it's constant. And then here, there'll be 100% probability if you see 1, 1, that it is balanced, okay? So, so that was a little bit of a deviation on the original Deutsch algorithm. The original Deutsch algorithm uses a trick, actually, that Carrie, I believe, talked about, which is a phase kickback. So here we've got our algorithm, we've got our first state, and this one is a constant function, so I'm just using an X gate here. And so it doesn't matter what comes into the oracle, it's always going to be constant. Now, so what we do then is actually throw this qubit away. And the phase after this oracle kicks back, and constructively, and in this case, if it's a constant, it creates perfect constructive interference here, which when you take it through a Hadamard operation, there's a 100% probability that it's going to be measure 0. But then, and so I can open this up in the Quark Simulator, and we can see that there's a 100% probability that it'll be 0. But then if I do a C0, which would make it a balanced, then we see 100% probability that it would be 1. And so here's another off, not really supported gate in most, this thing wasn't mentioned, but this one is, if this is a 0, then we flip this. And so we see that even with that, that's another balanced one, and there's an amplitude of 1. Sorry, the probability of 100% probability that this will be, that 1 will be measured, and so it's balanced. So then we have Deutsch-Jozsa algorithm. So that's a generalization of the Deutsch algorithm, and it was proposed in 1992. And it's the same thing as what I just showed you, except that they can be multiple inputs. So let's say that we had 3 wires coming in the into the everything but the ancilla here. We have 3 wires coming in. And then so that we have 3 inputs, we have constant, or this could be a constant function, and then we have balanced. Evens is going to come up with 0, odds will come up with 1 in this particular balanced function, and the opposite in that balanced function. And how many queries would it take of the oracle? Classically, well, it would be, in this case, it would be 5. So you would do 4 queries, which was half of the combinations that could come in, half of the inputs, and then add 1, and then you figure out which one it is. But quantumly, it's going to be just 1, and so it's exponentially faster. And so opening this up in the Quark Simulator, we have everything that we had in the Deutsch algorithm, but we're just adding the generalization, adding input bits here. Here we have a constant oracle. The constant oracle is simply, down there we can see that I just built a constant oracle, which is just an X gate at the bottom. And then this phase kickback then causes, with constant, it causes perfect constructive interference, which then when you send them through the Hadamard's, 100% probability that it's going to be 0, 0, 0. And so according to Deutsch-Jozsa algorithm, then if you measure 0, 0, 0, then it's constant. But then if we replace that with balanced, and balanced I'm just using a C0 here. You can see down here that's a C0. Then we see, because of the phase kickback, there's perfect destructive interference. And so you take these, these states are the plus state, the minus state, and you send them through Hadamard's, and you're going to get something other than 0, 0, 0. The reason I say something other than 0, 0, 0 is if you measure 0, 0, 0, it's constant. But there could be all sorts of different ways you could create this oracle for a balance. Let's say like this. Well, we get this. We're going to measure 0, 0, 1. But let's say we do it this way. Okay, here we're going to measure 0, 1, 0. But it's not 0, 0, 0. So you measure 0, 0, 0, it's constant. If you don't, it's balanced. So then, okay, colleagues mentioned Quill. Quill kind of reminds me, I've mentioned this to my colleagues. Quill, so some of you remember like days of really simple microprocessors like Zilog 80 or 8080 or whatever. So Quill kind of reminds me, it has the elegant simplicity of that kind of thing, where you can understand all the instruction sets, and you can kind of, to use 90s vernacular, you can pwn the thing, right? And so, so here is a Quill program for the oracle, for the constant. So this is Deutsch-Jozsa. with a constant oracle. And then here, and then we measure, with 1.0 probability that it would be 0, 0, 0. And then this is for a balance. Here we're using the C0. And in the quantum computing community, developers that are either converting from classical to quantum or doing both or whatever, there's this computer science student from Tricur, India, at the TKM College of Engineering that actually created a web-based circuit simulator that uses on the back end Forest. And so it generates Quill, and it also uses Forest to evaluate each level of the quantum state in the circuit. And so I'll just show you a really quick demonstration before we go here. Here's his quantum circuit simulator. Here I've got the DeutschJozsa algorithm in here. It's the constant. And so here's the Quill program that it generated down here. But then I can go here and say, well, I want a C0 here. And the target bit, I'll say, is 3. And so now we have a C0, which makes it a balanced. And I'll go ahead and click this check mark. And then it's going to go to, use the Rigetti API, hit Forest, generate the Quill program here over on the left, which we see the C0 here. See the C0 here. And then also generate all the superpositions that are going to be in each of the layers of that circuit. And so it's pretty cool. You can see his web-based simulator. Here's the GitHub link. This is his Twitter handle. And then here's a Medium blog post that he did. And so that's all I have. But thank you very much for your attention. If you have 1 or 2 questions.